Alright, so to start this video off, I just want to quickly jump back to that last example and revisit some of those key steps and actually use that example to springboard us to the idea of trying to establish or find this general solution of a given system of two linear congruences. So in this situation, I was in fact trying to solve one of these systems of two linear congruences. You can see that my first congruence is of the form x had to be congruent to 2 mod 3, and that second congruence was actually of the form that x had to be 3 mod 5. So in this case, we mentioned as we went through this that everything was built up out of this idea of that 3 and the 5. The kicker here was that those two numbers are in fact relatively prime. In this situation, actually, I know a little bit more because I know that 3 and 5 are actually prime numbers, which is actually going to give me information that they're relatively prime. But all I need to know is that they're actually relatively prime. The fact that they're prime just made some of the computation a little bit easier for me because they're not such massive numbers. So we'll get to some more examples that are going to have larger numbers, and on some of your activities, you'll actually have to start seeing these larger numbers come into play. But it's actually kind of a good springboard to see what's going on with the small numbers, because we can sometimes guess to see what all the little solutions are supposed to be. So in this case, if I know that I have two numbers that are in fact relatively prime, I can invoke this Bézou's theorem. So this Bézou's theorem is going to say that I can actually find these special little numbers. In this case, I can find a number s and I can find a number t, such that if I create this nice little linear combination of the form 3s plus 5t, it's going to kick out a 1. So back when we were first doing these things, I actually looked at these things as being x's and y's, but because I have x's up in my system, I want to use other variables. In this case, s and t seems to be a nice little pair. So in this case, I can actually use this extended Euclidean algorithm to actually go and try to find those things. So in some of your problems, you're actually going to first have to run this extended Euclidean algorithm to actually identify what those things are. And then once you have those, you're going to be able to apply this Chinese remainder theorem to actually solve these things. In this case, those numbers weren't so bad that you could actually just look at the thing and say, oh, if I take 3 times 2, it's going to kick out a 6. And if I take 5 and a negative 1, it's going to become a negative 5. And if I add those two things together, I do in fact get a 1. So this becomes our crucial, super important step in the middle of this thing. The idea is that if you look at this equation, if you reduced it modulo 3, this first component would disappear, and you'd have something that looks like 5 times negative 1 is going to be congruent to 1 mod 3. But the idea is that I don't want a 1 mod 3, I want a 2. So what I'm going to do is I'm going to take that 5 and the negative 1 and multiply it by a 2. Likewise, if I look at this equation up here and reduce it modulo 5, well, this thing is going to disappear modulo 5, and I'm going to be left with something that looks like 3 times 2 is going to be congruent to 1 modulo 5. I don't want a 1 mod 5, I actually want it to be a 3. So what I'm going to do is I'm going to multiply this 3 times a 2 by a 3. So in this case, if I add those two things together, it's going to create this nice little number. In this case, that number is going to be an 8. And I know that that's going to give me at least one solution for this system. The idea is, though, if I look at those numbers 3 and 5, if I add anything that's of the form of those two things multiplied together, in this case a 15, and I could add as many 15s as I'd want to, it's not going to deter the fact that I'm going to actually have the idea of being a 2 modulo 3, as well as a 3 modulo 5. So the general solutions to these things are all going to be of the form 8, and then I can add or subtract 15 as many times as I want to, because I know that 15 is going to be a 0 in both the mod 3 setting as well as the mod 8 set, or the mod 5 setting. So what I want to do in this situation is I want to slowly try to generalize this. So I want to start to think about removing things. So the first thing that I'm going to remove is knowledge about what s and t have to be. So here's going to be the idea that my general solution of my x is actually going to look like this. So it's 2 times 5 multiplied by whatever that t has to be. Likewise, that second component is going to be a 3 times a 3 times an s. In this case, my s happened to be a 2. So what I want to start to do is I want to start to think about what is a solution to a system that looks like this. So in this case, I want to change the 2 to just some general a, and I want to change that 3 to some arbitrary moduli. So I'm just going to call this thing an m1. Likewise, I want to see the second thing, which is going to be of the form, let's say, an a2, and my moduli is going to change as well. It's going to be, let's say, an m2. So what's going to happen in this situation is that anywhere you see a 5, so in this case, I tried to outline these things all in blue. So all of those 5s are going to change to m2s. So my general solution to this thing is then going to be of the form x. I'm going to put in a little m2 here. There's going to be a t. Likewise, anywhere I see an m1 or anywhere I see a 3, those are going to change into an m1. So you see all these little 3s floating around. So in this case, I'm going to have this red 3. So there's going to be an m1 there, and there's still going to be this s. And then I'm going to bring about these a1s and a2s. So in this case, you can see that little 2. that was the part that had to be multiplied by this blue 5. So in this case, my 2 is being played by the role of this a1, and I know that little a1 is going to have to multiply over here. So in this case, if I put a little a1 in front of it, it's going to match with what I have over there. Likewise, if I look at this a2, it's the same thing as that black 3 in this case. So it's not the red 3 in the moduli, so it becomes kind of tricky when you're trying to change these colors up. But the idea is that that a2 is that little 3, which is the 3 that came into play right here. So my general solution is going to look of the form a1 multiplied by m1 multiplied by this t plus an a2 m1 multiplied by this s, and that's going to be reduced modulo m1 multiplied by m2. In this case, the s's and t's, they're going to come from this nice little fact that I have up above. So I'm going to have that this m1 multiplied by my s plus my m2 multiplied by this t should be a 1. So if you have those two things together, you can easily just read off what your solutions are actually going to be. So that becomes the really slick trick, is that it's a little bit of build-up, but once I actually have that thing created, it becomes really easy to solve these things. So this slide is just going to outline the actual result that I just kind of hand-waved myself around, the idea of how can I actually see these solutions. So what's going to start is I'm going to start with two numbers, in this case m1 and m2. They have to be relatively prime. That's the kicker in all of this. If I know they're relatively prime, I'm going to have these special values of s and t, such that m1 times s plus m2 times t, that is in fact going to kick out this 1. So that's using this Bézou's theorem to actually find those, or actually have knowledge that those s's and t's actually exist. So then in this case, if I'm looking at trying to solve this system, so in this case, x has to be congruent to a1 modulo m1, and x has to be congruent to a2 modulo m2, what I can do is I can just create this nice little solution. So in this case, I'm going to have those two little components added together, and it's going to be reduced whatever those two things are multiplied together. So all right, so let's go ahead and see if we can actually apply this thing to at least try to solve one of these things. So in this case, I'm going to be looking at trying to solve this congruence, or the system of congruences of the form x has to be 5 mod 7, and x has to be 3 mod 9. So in this case, my little 7 is going to become my m1. The 9 is actually going to become my m2. So what I need to know is I need to know that these things are relatively prime, which in this case they definitely are. So what's going to happen is that I'm going to be able to find these s's and t's to give me this nice connection that's going to say, what way do I have it? So I'm going to have a 7 times an s plus a 9 times a t is going to equal a 1. So for right now, I'm just going to say what they actually are, and then we're going to come back to actually showing how I can find those s's and t's. So in this case, I know that 7 times a 4 plus a 9 multiplied by a negative 3, those two things added together are in fact going to give me a 1. So at this stage, my 7 is going to become my m1, the 4 becomes my s, the 9 is then going to be my m2, the negative 3 is going to be my t. So I have all 4 pieces that I need to actually go ahead and actually solve this thing. So what I'm going to do in this situation then is I'm going to view this x. Well, I'm going to have my 5 is going to become my a1, my little 3 is my a2. So now I can push all of these things together. So I'm just going to literally plug all of these things into this little solution that I have, and then I'm done. So it's a lot of build up, but at the end of the day, all I need to know is I need to know how to actually apply this little formula. So in this case, I'm going to have a1 m2 times t. So I need to pull off those 3 things and actually merge them all together. So let's see if we can do that. What do we got in this case? So I'm going to have an a1, which is a 5, and then I'm going to have an m2, right? That's the next thing that comes into play, m2, which in this case is going to be my 9. And then at the end of the day, what am I going to have? I'm going to have my t, which is a negative 3. That's then going to be added to an a2, which I know in this case is going to be a 3, multiplied now by my m1 times my s. So it's going to be that 7 times a 4. And this is going to be done modulo those two things multiplied together. So a 7 and a 9. So in this case, I'm going to have a1, this is my m2t, plus an a2 and an m1t. So that's exactly coming from right here. All right, so now I just got to simply reduce this thing, and hopefully I don't lose a bunch of negative signs and get something that's somewhat nice. So in this case, if I multiply those first 2 things together, those first 3 things, I guess in this case, it's going to kick out a negative 135. Those things over there are actually going to kick out something like an 84. And this is going to be done modulo. Well, if I actually multiply those things together, it's going to kick out a 63. I could simplify this a little bit more, so if I wanted to actually add these things together, it's going to kick out a negative 51, and that's still going to be done modulo 63. And at the end of the day, if I didn't want to work with this negative 51, I could add a 63 to it. So this is actually the same thing as saying 12 modulo 63. So in this case, all of these solutions to this system are going to be of the form x should be 12, and then add or subtract 63 as many times as you want to. So if you go up and actually test 12 into this thing, you do in fact see that it's going to work. If you look at 12 modulo 7, what's going to happen is that if you subtract a 7 from 12, you do go down to a 5. Likewise, if you take a 12 modulo 9, it's going to kick out a 3. So like I said, once you have this equation right here, the rest of the process is pretty slick. You just got to plug things into their correct bins, and you go from there. The challenge then is to actually find out what S and T have to be. And the way that we can actually do this is by running this Euclidean algorithm and then backfilling it and using this extended Euclidean algorithm to find those key little values. So in this case, if I wanted to run this thing on the pair 9, 7, and I'm going to put 9 first because it's the larger number, so it becomes a little nicer to run this process. So what's going to happen is that I have to try to see how many times does 7 go into a 9, and we know that it's going to go in there once because 1 times 7 is 7, and I'm going to have a remainder of a 2. So that's going to leave me with a new pair of 7 and 2, so a 7 and a 2. And then I rerun this thing on 7 and 2, and I'm going to have 7. 2 goes into 7 in this case 3 times, and you can see, oh, there it is. There's my nice little remainder of a 1. And in this case, my new pair is going to be a 2 and a 1. And if you wanted to, you could run this one more time to really properly see that, hey, I am going to have a remainder of a 0 at the very end, which is going to say, okay, you can stop, and then you go back to that last non-zero remainder. So in this case, it is another solution to actually say that those two numbers, 7 and 9, are in fact relatively prime. But what it's good about is that it's actually going to give me information on how to find those special numbers S and T. So in this case, I can solve this thing for a 1, which is going to say 7 minus 3 times 2. And now I'm going to build off of that little 2. So I'm going to substitute that knowledge of what 2 is from above into this little 2 right here. So in this case, I'm going to have a 7 minus a 3, and then a 9 minus 1 times 7. Distributing is going to give me a negative 3 times a 9 plus a 3 times a 7, which is going to give me that 4 times a 7 minus a 3 times a 9. So in this case, what I see then is that if I write this as 7 times 4 plus 9 times negative 4, I get exactly what I saw on that last slide. The idea that this 4 is my S, here's my T, and then I can stuff all of that back into this formal definition that I have before, and I know how to solve any of these systems of two given congruences. The idea is that you just have to find S's and T's. Once you know S and T, you plug in what you know for A1, A2, M1, M2 into this little ordering thing. Be careful on how these things get paired together. The A1 goes with the M2, and the A2 goes with the M1, but then at the end of the day, you have what your solution is. So it's a pretty slick little process. It takes a little bit of build up to actually get there, but once you have it, it's really easy to work with. You just got to do this extended Euclidean algorithm to find those pair of numbers, in this case S's and T, and then you backfill and you just plug in whatever you know. And at the end of the day, you actually get something that you can actually test. So in this case, we know that 12 works, so we're at least happy to say, yes, I've confidently done this. So the next video, we're actually going to push this idea back up to showing this thing for a larger system. So in this case, if I want to look at this thing for 3 given congruences, we're going to see how all of those little pieces come together. If you are interested, I do also have this kind of more formal proof of this Chinese remainder theorem for 2 congruences. The idea is that I took the proof for that first example that we just did, and I honestly just hit copy and paste. I changed all those little 3's to M1s, and I changed all those little 5's to M2, and I even kept all the coloring the same. So the idea is that you can run through this full formal process and you're still going to see this nice little solution at the end of the day. So if you're interested, you can go through that. I'm not going to make you show any of these things formally or anything like that. I just want you to kind of see how all those little building blocks get put together to actually create these nice little solutions. And then once you have it, you can go attack any of these problems.